one from freshman, one from sophomore, one from junior, one from senior. So what do? We just multiply them. Right? We just multiply 3 times 4 times 5 times 2 equals 120. But be very careful of the wording, right? We do choose 4, and one from each class. That's important. One from each class. If anyone has any questions at any moment, so feel free to stop me, or you can speak up, or you can type in the chat. So we just multiply all the, Catherine is saying, so we just multiply all the numbers, all the outcomes, but also be very careful with the wording. You see example 2b, right? Without saying consisting of one person from each class, the question will be different. And this one, we can apply counting principle because of this, because we choose 4 and 1 from each class. Okay, that's the key point. So we can apply counting principle. Let's say this example. How many different 7-place lesson plates are possible if the first 3 places are to be occupied by letters and the final 4 by numbers? If it says multiple people of each class, would you multiply the answer by that number? What do you mean? What do you mean multiple people?
You said that it was 1 person per class, and that's why you were getting that answer. So if they were asking, let's say 2 people per class, would you times that answer by 2 then?
No, that would be totally different question. But for us now, not to worry about that. All right. For us, what's important is this. So out of these 4 classes, we want to choose 1 from each. Okay. Don't think about anything else yet. So we'll consider that kind of question later on. For now, just remember when we apply counting principle, so this condition has to be satisfied. We have 4 classes, and we want to choose 1 from each class. Okay, let's see this one. So lesson plates, we have 7 places, and the first 3 we want to be letters. Letters means English letters, and the first 3 is English letters, and the last 4 are numbers, digits. So how many letters we have? 26, right? So I have 26 A, B, C, D up to Z. We have 26 letters to use. How many digits we can use? From 0 to 9, that's 10 digits. With 0, 1, 2, 3 up to 9, we have 10 digits to use. We have 26 letters to use. So how many different plates we can make out of these 3 letters and the 4 numbers? Well, letters, we have 26, 26, 26, right? Which means it can be repeat, because it doesn't say it cannot be repeat. So we could have F, 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 6, 6, 6, 6, right? It can be repeat. So 7 places. So let me actually go to whiteboard for this. So we could draw 7, 1, 2, 3, 4, 5, 6, 7, right? So the place has 7 places, and the first 3 are letters. And the first one we have 26 choices. Second one we also have 26 choices, because the question didn't say cannot repeat, right? So if we didn't say cannot repeat, so we assume it can be repeated. And the third one, we still have 26 choices. We can choose any letters, right, out of 26. Then these 4 spots has to be numbers. Numbers from 0 up to 9, we have 10 digits, right? 10 digits. So that means I have 10 choices. It can repeat 10 choices, 10 choices, 10 choices. By counting principle, I multiply them, right? The first one, I have 26 choices. The second one, I have 26 choices, so on and so forth. I multiply them, right? Of course, it's a big number. So it's a big number, right? It's 175,760,000. Let's see 2D. How many functions defined on endpoints are possible if each function value is either 0 or 1? How many functions defined on endpoints? So that means the domain we have endpoints, right? But the function value, the range, we only have 0 and 1. Counting principle, right? The domain we have up to n points, so n. But the domain we have 2, we have 0 and 1. So we have 2 raised by n possible functions, right? Because range we have 2. And the first one we have, the domain we have n. Anyone has questions for this? You could draw big oval shape, right? You have n in the domain. You have 2 in the range. So how many possible functions you can make? You can make 2 to the nth power, right? Because you have 2 times 2 times 2 times 2 times 2. How many times? N times, right? Because each one you have 2 choice. You have two functions, right? The point 1 either goes to 0 or goes to 1. You have 2 choices. Point 2 either goes to 0 or goes to 1. 2 choices. So on and so forth up to n. N can go to 0 or n can go to 1. So you have 2 times 2 n times. That's 2 raised by n. Let's see this one. In example 2C is this one, the lesson plates. How many lesson plates would be possible if repetition among letters or numbers were prohibited? So that means we cannot repeat the letter, we cannot repeat so it's different from this now. So if we cannot repeat, so the first one, 26 letters, out of 26 letters, 1 is used. So how many left? It's only 25, right? So the second one, we only have 25 choices now. Now 2 letters are being used because we cannot repeat. So how many letters left? 24. Same thing for the digits. If 1 is used, it cannot repeat. So the first number, we have 10 choices, but the second one, we only have 9 left. Then we have 8. Then we have 7, right? You see the difference between, repetition is allowed and the repetition is not allowed. So if repetition is not allowed, we have a lot, the number, the choices is a lot less. So that becomes 26 times 25 times 24 times 10 times 9 times 8 times 7. You see, it's how much smaller, right? It's more than half less. So this one is this number, this one, this number, right? So this one allows repetition of the letters and digits. This one does not allow repetitions of letters and digits. Anyone has any questions? So those use the counting principles. All right, let's keep going. Permutations. And one thing is called factorial. Well, n factorial means n times n minus 1 times n minus 2 up to 1. Right. Think about the 3 factorial is 3 times 2 times 1, which is 6. 1 factorial is 1, 0 factorial is 1, 2 factorial is 2. So let's see this one. How many different batting orders are possible for a baseball team consisting of 9 players? How many different batting orders are possible, right, for 9 players? So you could think as we have 9 spots, 9 places. The first one we have 9 choices. The second one we have 8. We have 7. We have 6. We have 5. So on and so forth. That's just 9 factorial. 9 factorial, if we multiply out, that's this number. So there are 9 factorial possible batting orders. Let's see this one. A class in probability theory consists of 6 men and 4 women. An examination is given, and the students are ranked according to their performance. Assume that no 2 students obtain the same score. A. How many different rankings are possible? 6 men and 4 women, so 10 people, 10 students, right? And then no 2 students have the same score. So how many different rankings or scores that are possible? Well, 10 factorial, right? Because 6 plus 4 is 10, and each one have different grades, so 10 factorial, different rankings or different scores. So there's 10 factorial, which we multiply as 10 times 9 times 8 until multiplied by 1, which is this big number. And B, see, if the men are ranked just among themselves, now it's different, right? And women just among themselves. So how many different rankings are possible? Well, that's different now. So if we rank men, so let's 6, that's 6 men, 1, 2, 3, 4, 5, 6. So I have 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial. And women rank themselves too. That's 4 times 3 times 2 times 1. Right? So 6 factorial and 4 factorial. Then by counting principle, we multiply them. So that's just 6 factorial multiplied by 4 factorial, which is this number. It's a lot smaller than 10 factorial, right? Any questions? Let's see. Miss John, let's see this example. Miss Jones has 10 books that she's going to put on her bookshelf. Of these, 4 are mathematics books, 3 are chemistry books, 2 are history books, and 1 is language book. Miss Jones wants to arrange her books so that all the books dealing with the same subject are together on the shelf. All right. So treating the same. So mathematics are together, chemistries are together, histories are together. All right. So how many different arrangements are possible? Similar to this one, right? Similar to this B. Right. So for the math books, right, we have 4 factorial ways, right? We can put 1 book, so out of 4, right, put 1 book first, then the rest of 3, 2, so on and so forth. Then 3 factorial for the chemistry books, 2 factorial for the history books, 1 factorial for the language book. Then by counting principle, just multiply. So 4 factorial times 3 factorial times 2 factorial times 1 factorial, right? 6,912 ways. Let's see this one. How many different letter arrangements can be formed from the letters P, E, P, P, E, R? How many P's we have? We have 3 P's, right? Or 2 E's, or 1 R. And of course, the P's are the same, right? 2 E's are the same. We'll only have 1 R. So if we think there's 6 factorial ways, but we counted more, because we have 3 same P's, we have 2 same E's. So we have to do the same thing as the above, right? Because we're treating the 3 P's are same, 2 E's are the same. So for P's, so we have to, in total, first we don't care about the same P's, the same E's. So we would have 1, 2, 3, 4, 5, 6 letters, right? That's a 6 factorial. But then we have 3 P's, we have 2 E's. That means we overcount. We overpermute. Well, 3 P's and 2 E's. So what do? We would do division. We would divide. So we do 6 factorial divided by 3 factorial for 3 P's, then divided by 2 factorial for 2 E's. All right. So here explains to you why is that, right? If we put a P1, P2, P3 for those 3 different P's, we see that, we overpermute, we permuted. If we do 6 factorial, that means we also permute P1, P2, P3, but those 3 P's are the same. We also permute E1, E2, but those 2 E's are the same. So what do? We do division, all right? Not subtraction, all right? We divide. So 6 factorial divided by 3 factorial divided by 2 factorial. So 3 factorial, 2 factorial in the denominator. So if we do the calculation, we get 60 possible letter arrangements. So how do we calculate the division? So let's see, we have 6 factorial divided by 3 factorial divided by 2 factorial. 2 factorial we know is 2, right? Because 2 times 1, just 2. 3 factorial, so 6 factorial is 6 times 5 times 4, then times 3 factorial. Right. Then this 3 factorial and this 3 factorial in the denominator cancel out. So 2 cancel out the 4 to be 2. 2 times 5 is 10. 10 times 6, 60. All right. Okay, so in general, if the repetition in groups, or if they're equally ranked in groups, so we would count how many in total, right? Divided by the number in each group. Well, of course, factorial, right? Factorial way. So N1 factorial, N2 factorial, and R factorial. So that's in general. Any questions for this example? Okay, let's see this one. Actually, they're the same, similar. Similar. You can go through those examples. Okay. So make sure you understand every example. All right. The exam questions will be very similar to the examples. Well, that's permutation, combinations. Okay. Permutation. Okay. What's the difference between permutation and combination? Permutation has order, right? Think about the plates, the lesson plates, right? If a number in the first place is different from the number in the last place, right? But combination doesn't care about order. Combination has no orders. It's just in a group. You can think in a group. So permutation has places, right? Has order. Combination is within a group, okay? In a group. Has no order to the members. So we use this notation, right? I believe you learned binomial theorem. Remember binomial theorem, we learned this combination notation, big parentheses. So this means out of n, choose R. Yeah. Out of group of n members, choose R members in a group. It's like, okay, out of a class of 20 people, choose 2 to be representatives. Right? Those 2 representatives are equally ranked. Has no order. But if we say out of a class of 20 students, we want to choose 2 students, but one is president and another one is a vice president, then the 2 people are not in the same group because one is president and one is vice president. So it seems like, you know, it has order, right? But if we choose 2 representatives, those 2 representatives are equally weighted. So combination is this. So out of n, choose R. That's n factorial divided by n minus R factorial divided by R factorial. Okay. So we have a counting principle. We have this. Okay. For permutation, we have to think about the repetitions. All right. Permutations, we have to think about repetitions. And the notation, I mean, combination, it just has this nice formula to follow with. Permutation will have to go by logic. Permutation, we could think of this one as what do you call it? As a formula. All right. So the n total members, we have n total members, and some members are repeated. Right. Maybe you have n1, n2, nr. So this would be the formula for permutation. And this is for combination. All right, so n factorial divided by n minus R factorial divided by R factorial. So let's see this example. A committee of 3 is to be formed from a group of 20 people. A committee of 3, no order, right? And from a group of 20 people. So how many different committees are possible? We just do combination. So out of 20, choose 3. There's 20 factorial divided by 20 minus 3, 17 factorial. You see, this is 17 factorial in the numerator, 17 factorial in the denominator already being cancelled. Then divided by 3 factorial, which is 3 times 2 times 1, which in the end, the 1140 possible committees can be formed. Well, I can change this question a little bit. I can change this question to be, out of 20 people, I want to choose 3 people, 1 to be the president, 1 to be the vice president, and 1 to be the secretary. So that would be different because 3 people would have different kinds of, you know, the order involved. So then what's the answer for that? 1140 times 3 factorial. Well, let's see. So we have 20 students, right? Now we have 3 things. So president, vice president, and secretary, right? So out of 20, I want to choose one president. I have 20, right? I have 20 choices because anyone can be. But once one is here, how many students left? I have 19 students left. And 2 students are chosen, I have 18 students left. So 20 choices for president, 19 choices for vice president, and 18 choices for a secretary. By counting principle, I multiply them. All right, so that's how many ways of choosing 3 people with different titles. Okay, so 20 times 19 times 18. Because when we do permutations, we do this way. All right, because permutations gives you places. You can always do these spots. All right. Okay, let's see this example. From a group of 5 women and 7 men, how many different committees consisting of 2 women and 3 men? And what if 2 of men are fielding and refuse to serve on the committee together? Well, let's see the first question mark. So out of 5, we want to choose 2, right? That's the many ways. So out of 5, choose 2 ways for women. Out of 7, choose 3, right? That's choices for men. Then what do? Then we multiply, counting principle, right? Multiply. So out of 5, choose 2. Out of 7, choose 3. Then we multiply them. Then we calculate to get 350. So that's for the first question mark. So there are 350 possible committees consisting of 2 women and 3 men. Now the second one says if 2 men are not refused to serve on the committee together, so what do? So 7 men in the beginning, 2 rejected. How many left? There's 5, right? The 5 left. So suppose 2 of the men refuse to serve together. Oh, 2 men refuse to serve together, right? That means if one is, out of those 2 men, if one is choosing, the other one, don't want to be in it. So total 7. So out of 2, choose 2. So let's think about this one first. So out of these 5, out of 2, choose 2. Out of 5, choose 1. What's this? What is this calculation? Because the total of 2 out of 2, choose 2. Out of 5, choose 1. That's 5 ways. 5 out of this 7, choose 3. So out of 7, choose 3. That's only 35. Let me quickly calculate this. 7, 6, 5, 3. Yes, so that's 5 times 7, 35 possible groups. Yes. So 3 contain both of this. It follows that there are 35 minus 5 equals 30. Okay. So this one is calculating how many ways, right? How many ways if those 2 men serve together? How many ways if those 2 men serve together? So out of these 2, choose 2, right? So out of these 2 men, choose 2. So choose both of them to serve together. Then how many left? There are 5 left. And because totally we choose 3, so from the rest of the 5, we only have to choose 1. So there are 5 ways of doing this. But out of 7, choose 3, there are 35 in total. So 35 ways, subtracting 5 ways the two men serve together, that's 30 ways. That's 30 ways, right? So 30 ways do not contain both the men. So the 30 ways those two men not going to work together. So there's still 5 out of 5 choose 2 for women. So what do? We multiply those two numbers. So out of 5 choose 2. If you calculate that equals 10, right? Because 5 times 4, 3 factorial, cancel 3 factorial. 5 times 4, 20. 20 divided by 2, that's 10 ways. So 10 multiplied by 30, totally that's 300 possible communities in this case. So this one like looks like exam questions. So you have to think a little bit, right? Everyone has any questions? Okay. All right, let's see. Okay, let's see this example. Consider a set of n atenuators which m are defective and n minus m are functional, and assume that all of the defectives and all of the functional ones are considered indistinguishable. How many linear orderings are there in which no two defectives are consecutive? Okay, this is a little bit complicated question. So let's just read the solution. Imagine that n minus m functional ones are lined up among themselves. So now, if no two detectives are to be consecutive, then the space between the functional ones must each contain at most one detective ones. So that is in the n minus m plus 1 possible positions represented, right? Just like this one. A good one, bad one, a bad one, good one, bad one, good one, because no two no two next to each other. So between the n minus m functional ones, we must select m. So that's n minus m plus 1. That's how we count, right? Then out of this many, choose m of them, possible ones. So we can use this combinatorial identity. This combinatorial identity is saying out of n, choose r. That equals out of n minus 1, choose r minus 1, plus n minus 1, choose r. So you can, maybe later on we can prove this identity. So this is just one of the combinatorial identities. So if we use this one, so this one can be proved, by combinatorial analysis. Okay, so you can read this later to convince yourself, all right? Binomial theorem we have learned already, right, in pre-calculus class. So x plus y binomial raised by n's power, right? We have n plus 1 terms. So k start from 0, n at n, that's n plus 1 terms. So the coefficient of each term is out of n, choose k. K start from 0, then become 1, 2, 3, up to n. So we have n choose 0, out of n choose 0, for x raised by 0, y raised by n, and so on and so forth, right? This is just short notation. This is short notation. So this contains n plus 1 terms. And you can also get this coefficient by Pascal's triangle. X goes ascending order, because the exponent of x goes from 0 up to n. The exponent of y, the second term, goes descending order, starts at n, ends at y raised by 0. So this is a proof of that, and you can go over yourself. Okay. So this is using the identity. This is a combinatorial proof for binomial theorem. Basically using counting principles and the combinations. All right, let's review this. We have done this before, right? Let's see in this class. So n is 3. Out of 3, choose 0 because k start with 0. The index k start with 0. So k goes from 0, 1, 2, finish at 3. So we have 4 terms, right? And n is 3. So the first term is out of 3, choose 0. Well, that's just one way, right? Out of 3 things, you choose nothing. That's just one way to do it. You don't do anything. X raised by 0, which is 1. Y raised by 3, right? It's just y cubed. Second term is out of 3, choose 1. Right? Out of 3, choose 1 is 3 factorial divided by 2 factorial divided by 1 factorial, which is 3. Then x raised by 1, because the k is 1 now. The index k is 1 now. X raised by 1, which is x. And the y raised by 3 minus 1, which is 2. All right, so y squared. The third term is out of 3, choose 2, which is also 3. It's the same as out of 3, choose 1. Then x raised by 2, the index 2. And y raised by 3 minus 2, which is 1, or which is just y. That way it looks easier to expand. I see. Compared to what? Compared to Pascal's triangle? Right, so we simplify a little bit, so we get a y cubed plus 3xy squared plus 3x squared y plus x cubed. So we can observe. You see, x goes ascending order, right? So the first one is x raised by 0, then x raised by 1, then x raised by 2, then x raised by 3. First term. So the exponent of first one goes ascending order. The exponent of y goes descending order. So y raised by 3, y squared, y, then y to the 0, right? So that's binomial theorem. Now let's see this question. How many subsets are there of a set consisting of n elements? Subset. We understand the subset, right? Or maybe I explain a little bit. So let's see if I have a set of 2 things, 1, 2. Right? How many subsets I have? I have an empty set, which means I choose nothing. I can make a set of 1. I can make a set of 2. And I choose both of them, 1, 2. All right. So 4 subsets. So usually it's 2 raised by n. N means how many members in the set. If I have 3, right, you can list of them. That's 2 raised by 3, which equals a subsets. All right. So 2 raised by n, a set has 2 raised by n subsets. And n is how many members in the set. How many subsets are there? Let's see this, right? This calculation. Since there are out of n, choose k subsets of size k, the desired answer is, so we'll let index k goes from 0 up to n, right? Out of n, choose k, because out of n, choose nothing, that's an empty set. Out of n, choose 1, that's just one member. Out of n, choose 2, the 2 members in the subset. Out of n, choose 3, so on and so forth, up to out of n, choose all of them. So that's a 1 plus 1 raised by n, 2 raised by n, 2 raised by n. Right? Can you see that's a 1 plus 1? Where does this 1 come from? Compared to this. Right? You don't see x raised by k, y raised by k, y raised by n minus k. Because only 1, so that's 1 raised by k, 1 times 1 raised by n minus k. Because this only has a coefficient out of n choose k. So that's why 1 plus 1 raised by n, which is 2 to the nth power. So this is a Q proof by binomial theorem. Okay. Anyone has any questions for this? Okay, I'm going to leave 1.5, 1.6 for next class. All right. If you like, you can go ahead of the class time. So next class, hopefully some of you can present. Right? Presentation serves as review. Anyone has any questions? If no questions, you're a free bird. You can go ahead to choose a couple of questions from each section. Okay, and start to do the question and prepare for your presentation for next class. So next class, we're going to talk about 1.5, 1.6. All right, if you have questions, I'm here. And oh, yes, you're a free bird. You're a free bird. You can go ahead, do your homework, and prepare for presentation next class. All right, have a good night. Yeah, Chanel, questions?
Just to make sure, for the homework and the presentation, we're doing 1.2 to 1.4?
Yeah, 1.2, 1.3, 1.4, yes.
Okay, thank you.
You're welcome. I'm going to stop recording.
Professor, for
Yes.
the whole chapter is like you choose 25 questions, right? Not like
That's right.
okay.
That's right. For the whole chapter, we choose 25 questions. Let's see, for the first one, we have, so introduction doesn't have any questions, I don't think. 1.2, so you have 5, 1, 2, right, you have 5 sections. So maybe choose a 5 out of each section. Okay, any other questions?
So, Professor, so from chapter 1, we have to do the problem from the theoretical exercises.
Chapter 1, don't do any questions of chapter. I don't think. Oh, chapter 1.
Yeah, I mean, like, from where we have to choose the problems, from the
Yes.
example.
Or not from the
exercises.
From the exercise.
Oh, okay. So
yeah, you see.
I see there are 3 parts, like problems and then theoretical exercises and then self-test problems. So,
choose from the problems.
From the problems, okay.
Right. Okay. Well, you have a choice. Theoretical exercise. You want to choose from this because this is more theoretical, more abstract. If you want to choose from here, that's fine too. Yeah.
Okay. Yeah. Okay. Thank you, Professor.
You're welcome. You can even choose from the self-test. All right.
Okay.
Choice. Yeah.
Okay. Thank you, Professor. Have a good night.
You're welcome. Have a good night. Any other questions? Tom, good to see you here.
Hi. Is
Hi.
the midterms are online?
Midterms are online. Midterms is online, will be online.
How would we like submit those?
I will let you know. It's like a homework, same way as homework.
Oh, is it timed?
Oh, no, I don't have time yet.
I mean, like the midterms are, we have a certain amount of time to do them.
Yes, class time, like 2 hours.
Okay.
Okay.